So we're still talking about solids of revolution, but we're going to talk about a different way of computing their volumes. This is called the method of cylindrical shells. And although we can still use the disk method in this case, people often find it conceptually easier to use cylindrical shells in the case that we're looking at. And well, if we had more time in the class, I would be a little bit more strict and kind of force us to be able to figure out which method to use independent of whether we're looking at a horizontal axis of rotation as we did last time, or a vertical axis as we are going to look at this time. But you know, there's only so much time and this is only of so much importance, so we're just going to deal with this case whenever we're looking at a vertical axis of rotation. So we've got a region in the plane that's bounded by a function f of x between the values of x, a, and b above the x-axis, and we're going to rotate it around the y-axis this time. And so this red region, we rotate around the y-axis, the vertical axis, and we get this red shape here, sort of this bundt cake sort of shaped thing. Great. And the way that we're going to compute the volume here is, instead of cutting it up into disks or washers or whatever, we're going to notice that if we take a slice of this area that is perpendicular to the x-axis, and we see what its path is around as we rotate the entire region around the y-axis, we get a cylinder. And using this idea that if we add up a bunch of areas together, we should get a volume. If we add up the surface areas of all the different cylinders that we get as we take different slices going from all the way from A to B and looking at the cylinders they generate, if we look at that, we should be able to recapture the area. And there is there's certainly some work to be done to justify that this is valid, in particular because we're talking about the surface of a curved surface, and it's immediately obvious that the surface area of a curved surface like this is going to give us the right thing. We can go through the work and make it work, but again, we're not going to because we've only got so much time. So let's recall what the surface area of a cylinder is. It's pretty simple. All it is the circumference of the circle times the height of the cylinder. We're only talking about the vertical surface area here, so just, you know, this part here. Anyways, so the circumference of the circle is 2 pi r, the height is h. If the radius of the cylinder is r and the height is h, so great, the area is 2 pi rh. So now here's our region that's bounded by f of x, x equal to a, x equal to b, and the x-axis. We're going to take some point x and look at the cylinder that the slice at x sweeps out. We need two things about it. We need to know what the radius is, and we need to know what the height is. Well, the radius is just the distance between the axis of rotation right here, which is the y-axis, and this point on the graph right here. Well, this point on the graph is x comma f of x, and its horizontal distance is therefore x. And that's the radius. And the height is just going to be the distance between this point up here and the x-axis. And well, again, the coordinates of this point are x comma f of x. So the height here is f of x, the y-coordinate, the vertical distance. So that means that the area at x, thinking of this as an area function of the cylinder at x, is equal to 2 pi x times f of x. Great. So that means that our volume is going to be the integral from a to b, right there, 2 pi x times f of x dx. Great, so it's the integral from a to b because that's what our region is between, 2 pi x f of x because that is the surface area of the cylinder at the slice x dx. Great. One nice thing about the method of cylindrical shells is that even if you're bounded away from the axis of revolution, you don't have to worry about subtracting off something for sort of the whole. The whole is taken into account of for just by the nature of the method. So let's find the volume of the solid generated by rotating the region bounded by y equal to x squared, the x-axis, x equal to 1 and x equal to 2, about the y-axis. So, great, here's our region. I think it's always good to sketch it out. Y equal to x squared. We're graphing between x equal to 1 and x equal to 2 above the x-axis. Great, that's our region. And when we rotate it, we end up with something that looks like this. It's like a cylinder with a sort of a bowl-shaped hole bored out of it, and then a cylindrical hole bored at the bottom. The bowl shape comes from this part right here. The cylinder kind of comes from this hole right there. Anyways, so the volume is just going to be by our formula, the integral from a to b, which is 1 to 2, of 2 pi times x, because x is what we're adding the cylinders up from 1 to 2 over, times f of x, well, and x is the radius of each cylinder. F of x is the height of the function, and, well, the function is x squared dx. So it's the integral from 1 to 2. You know, I often like to pull out the 2 pi just to, I don't know, make things less messy, I suppose. So it's the integral from 2 pi times the integral from 1 to 2 of x cubed dx. The antiderivative of x cubed is x to the 4th over 4. That's going from 1 to 2. So this is going to be 2 pi times 2 to the 4th over 4 minus 1 to the 4th over 4. And that's going to be 2 pi times 2 to the 4th is 16 divided by 4 is 4. So 4 minus 1/4 is 3.75. So that's 7.5 times pi. Here's question 1. Find the volume of the solid generated by rotating the region bounded by y equal to the square root of x equal to 1, x equal to 4 on the x-axis, about the y-axis. Okay, so let's find the volume of the following solid. And I'm not going to write all of the business right now because, well, it takes a lot of time. Anyways, so we're looking at the solid bounded by y equal to sine of x squared on the x-axis, and it looks like we're looking at the region bounded between the first two roots of the function, or the first two non-negative roots of the function. Well, so this one we have to figure out the x values. So the question is, when is sine of x squared equal to 0? I know that sine is equal to 0 at 0 plus or minus pi, plus or minus 2 pi, etc. So this guy right here seems like it should be x squared equal to 0, which is x equal to 0, sure. And then the first time that we're going to hit the x-axis again after 0 should happen when x squared is equal to pi, because that's the first time that sine is equal to 0 after we go to the right. So that means that x is going to be plus or minus the square root of pi, and since we're looking at positive values of x, it's going to be the square root of pi. So this means that the volume is equal to the integral from 0 to the square root of pi of 2 pi times x times sine of x squared dx. In this chapter, in this section rather, when we're talking about these cylindrical shells, if we don't have x times a bunch of powers of x, then we're going to have x times some function, and generally that means we're going to have to do some sort of substitution, because that's really the only game in town right now when we try to do an integral where we have x, you know, the product of two functions. And here this is really set up for it. So what we can do is, I see x squared is inside of sine. That really suggests that I try u equal to x squared. Du is equal to 2x, and look, I've got 2x, well, 2x dx, I've got 2x dx right here. So right there is du, and that's u. So v is equal to the integral of pi times sine of u du. The pi doesn't become part of anything, it just gets to hang out. Again, I always suggest that we replace the limits. When x is equal to 0, u is equal to 0 squared. When x is equal to root pi, u is root pi squared. So those become 0 and pi. So pi, 0. Great. So the antiderivative of sine is negative cosine, so I get negative pi cosine of u going from 0 to pi, which is negative pi times cosine of pi minus cosine of 0, and cosine of pi is negative 1, cosine of 0 is 1, so I have negative pi times negative 2, which is 2 pi.